Did you know that this bowling ball in front of me is exerting a force on this mini volleyball? And did you know that at the same time, this mini volleyball is exerting a force on this bowling ball? Hi everyone, I'm Mr. Pinola, and what I just told you is 100% true. In fact, one of the 4 universal forces that we talked about last time is at play here. Do you know which one? It's the force of gravity, otherwise known as gravitational force. This bowling ball is exerting a gravitational force that is pulling the mini volleyball towards it. And this mini volleyball is exerting a gravitational force that is pulling this bowling ball towards it. No, these are not planets, but yet they can still exert forces of gravity. And today, we're going to take a look at what that truly means. So let's start with the most basic question. Why can these 2 objects exert gravitational forces? The answer is simple. It's because they both have mass. Remember, mass is the amount of matter that something has. And matter is made up of atoms. The bowling ball and the volleyball both have atoms that make them up. And therefore, they each have mass. And therefore, they're each going to pull on each other, just based on the fact that they have mass. In fact, my body has mass too. So technically, I'm pulling on the bowling ball and the volleyball, and they're both pulling on me at the same time. So now let's tackle the second question. If these balls are putting forces on each other, why aren't they moving? Well, the answer is the fact that gravitational force, even though it acts very well over far distances, is ultimately not very strong. Now, the Earth exerts a big force of gravity on us, but that's because of how big the Earth is. Compared to the size of the Earth, these 2 balls are minuscule. They are really, really tiny. And therefore, they're not going to be able to exert much force. So even though the bowling ball might pull on the volleyball, just a little bit of friction with the volleyball on the table is enough to keep it from actually moving towards the bowling ball. And it's the same thing with the volleyball. Even though it's putting a force on the bowling ball, that force is so weak that it's not even enough to overcome the friction between the bowling ball and the table, and you won't actually see anything move as a result of these gravitational forces. So now let's tackle a third question. Which is bigger, the force that the bowling ball pulls on the volleyball with, or the force that the volleyball pulls on the bowling ball with? It might seem surprising, but let's think back to Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. Or as we learned about it, for every action force, there is an equal in magnitude and opposite in direction reaction force. So if the bowling ball pulls on the volleyball, that's my action force. The reaction force would be the volleyball pulls on the bowling ball. And Newton's third law says that those forces are equal. So if the bowling ball pulls on the volleyball with 0.5 newtons of force, then the volleyball will pull on the bowling ball also with 0.5 newtons of force to satisfy Newton's third law. So we know that the bowling ball pulled on the volleyball and the volleyball pulled on the bowling ball because they both had mass. And we also explored that they pulled on each other with equal amounts of force. Again, if the bowling ball pulled on the volleyball with 0.5 newtons of force, then the volleyball would pull on the bowling ball also with 0.5 newtons of force. That's called universal gravitation. Remember, gravitational forces are an example of universal forces, forces that are all around us in all parts of the universe. So it's true, any object with mass will exert a pulling force on any other object with mass. In fact, right now, this water bottle has mass, and I have mass. So technically, if I were to put my water bottle on the blackboard right here, it would be pulling me towards it, and I would be pulling the water bottle towards me. But remember, gravitational force is the weakest of the four universal forces, and because of the presence of things like friction and air resistance, we won't actually move as a result of those forces. So we know that these objects are going to put forces on each other, but the forces won't be that strong. But what could I do if I actually wanted them to pull on each other with a lot of gravitational force? Well, we could do two different things. In order to increase the amount of force that we would feel, we could increase the mass of the objects. That's why the Earth pulls on you so strongly. It's because the Earth is so massive, and so it's able to exert a tremendous gravitational force. The other thing we can do is we can decrease the distance. Right now, I kept those two objects very far apart, but if I was to bring them closer together, then they would put more gravitational force on each other. So any object with mass will attract any other object with mass using a very small amount of force. And if I wanted to make that gravitational force bigger, I could increase the mass of one or of both of the objects, or I could move the objects closer together. So here's a pretty bad diagram of the Earth and of the Moon. And as we talked about in our last video, these are just large examples of what the volleyball and the bowling ball were doing to each other. The Moon is going to pull on the Earth with a certain amount of force, and the Earth will pull on the Moon with the same amount of force. Now, we can very clearly see the effect of Earth pulling on the Moon. The Moon constantly goes around Earth. It orbits us. But what about the Earth? If the Moon is pulling on the Earth, how do we notice that? Well, the Earth is so massive, so it doesn't really respond too readily to the force that the Moon is putting on it. However, there are some dramatic examples. Let me show you one of them now. Here is a location in Canada that you're viewing a picture of. This is called the Bay of Fundy. Now, it might not look much like a bay because this is all dirt. However, I want you to watch this time-lapse video of the Bay of Fundy. As the Moon revolves around the Earth, in some places it gets a little bit closer to our planet. And due to the motion of the Moon, and also a little bit of the motion of the Sun, the water of Earth can get pulled as a result of gravitational force. So watch the water in the bay as the day goes on and the Moon moves around. Remember, we can't see the Moon during the day, but the Moon is still exerting forces on the Earth, just like the Earth is exerting forces on the Moon. Let's have a watch. As you can clearly see from the video, there is a dramatic difference between high and low tide at the Bay of Fundy, and it's caused by the position of the moon. As the moon moves closer towards the Earth, there is a stronger gravitational pull. And based on the positions of the moon and of the sun, sometimes the layer of water surrounding Earth, all of our oceans, rise a little bit. And the rising ocean causes tides in bays, such as the Bay of Fundy. In fact, when watching the video, did you happen to notice that there were a couple of people walking along the bay before the water filled in? They wouldn't be able to complete this walk now, but they were able to at the time because they knew about the cycles of the moon, and they knew based on the position of the moon that the tides would rise and lower. So, even though we can very clearly see the moon orbiting around Earth, there is also some very clear evidence that the Earth pulls on the moon at the same time. I'd like to show you one last example of universal gravitation. And that has to do with something that you might see in the sky. It's called a satellite. Maybe you've heard of satellites before. I'm going to draw a pretty poor diagram of a satellite that is orbiting around Earth. There are many, many satellites that orbit Earth. Perhaps it's the reason that you get good cell phone reception, or perhaps it's the reason that you get your satellite TV at home. And so the satellite will make a path like this around Earth. That's called its orbit. But how does the satellite follow in its orbit? Well, the key is actually universal gravitation. The satellite is always moving in a straight line. However, the Earth is constantly trying to pull the satellite towards it. And as a result, the satellite ends up following a curved path. The satellite wants to move straight, but thanks to universal gravitation, the satellite is always being pulled towards the center of the Earth. And it's that force constantly pulling the satellite towards the center of Earth that causes it to ultimately go around in a circle. Do you know what that force is called? Any force that causes something to move in a circle? Well, it's given a name that is the centripetal force. And a centripetal force is just this: any force that always works to bring an object towards the center of another object that causes it to move around in a circle. And that's what's going on here. The gravitational force that Earth exerts on the satellite is drawing the satellite towards the center of the Earth. But the satellite doesn't actually fall towards Earth. It follows a circular path because of its original moving speed. It ends up just circling over and over again. Let's now take a look at a real-life example of how a satellite moves in the classroom. So maybe I lied a little bit. We're not going to actually see a satellite, but we're going to see satellite motion shown with this car. Notice that this car is attached by a string to this table. If I turn the car on, it's going to try to move forward, but the string is going to constantly pull the car towards the table. The string is the centripetal force trying to bring the car towards the center. But as a result, between the combination of the car's speed and the centripetal force trying to pull the car towards the middle, it'll follow a curved path. Have a watch. Notice it moves around in a circle as a result. But what happens if we were to suddenly get rid of the centripetal force? What happens if Earth suddenly stopped applying a gravitational force to a satellite orbiting around it? Well, the object would then just go off, moving in a straight line at the speed it was originally moving. Let's try that out. I'm going to start my car way back over here, and I'm going to allow it to follow a curved path. But then I'm going to use this pair of scissors to cut the string. Watch the direction of the motion of the car once I take away the centripetal force and cut the string. Notice now it moves straight. As you can see, the car was sort of like a satellite orbiting Earth. It wanted to continue moving straight, but the centripetal force from the string was always bringing it towards the center. This is the same way that the gravitational force that Earth applies to a satellite or anything else that orbits it, like the moon, causes that object to continue in circular motion. I hope you learned something today about gravitation or gravitational force. Remember, we call it universal gravitation because any object that has mass can apply a gravitational force to any other object that has mass. And that force becomes stronger as the objects get more massive and as the objects move closer together. We also see that gravitational force can act as a centripetal or a center-seeking force that will cause an object to orbit or to revolve around something else, just as a satellite would do around Earth, or as the car from the last example did around the table. Remember, in order to have gravitation, you must have mass. And even though gravity works at the farthest distance, it is still the weakest of the four types of universal forces, unless the masses are extremely big and the distances extremely short. Thanks for watching, folks.